Hello everyone, in this video we're going to see an impossibility result that pertains to registers. The field of concurrent computing is filled with impossibility results, and impossibility results are extremely useful, among others because they elicit the limitations of real systems, and therefore we can use them to avoid kind of chasing impossible designs, let's say. So here's the transformation that uses a single reader, single writer, regular register, kind of builds an atomic single reader, single writer register. And what's interesting to notice is the following. So this regular register of the transformation, this base register of the transformation, kind of stores a timestamp and a value. What is interesting to note here is that kind of this timestamp can become arbitrarily large. So the underlying regular register kind of that we use for this transformation is an unbounded one. The second interesting thing to notice in this algorithm is that the read operation does not perform any writes, but only reads kind of what is being contained in this regular register. So in this video, we'll prove the following impossibility result: that we cannot have a single reader, single writer atomic register implementation that is based on finite number of bounded regular registers, and where the reader does not write to these registers, to these regular registers. So this is what we're going to prove in this video. Let me just briefly say that this impossibility result and the proof that we're going to describe in this video is taken from Professor Karolos' book, Algorithms for Concurrent Systems. To prove this impossibility result, we first have to introduce an auxiliary notion, the notion of a digest. So consider a sequence S, which is a finite sequence of values. So a digest of sequence S is a new sequence D, which is possibly shorter than the original sequence S, and that in some sense summarizes sequence S. So what do we mean by this? This summarize notion kind of means the following three things. First, S and D have the same first element as well as the same last element. Second, no element appears twice in D. And final and third one is that any two consecutive elements in D are also consecutive in S. To make this more clear, let's give an example. So assume we have sequence S to be 1, 2, 1, 3, 4, 2, 4, 5. Now a possible digest of sequence S could be D1, where D1 equals 1, 2, 4, 5. So as we can see, the first element is the same, the last element is the same. Every two consecutive elements are also consecutive in S. And no elements appears twice in D1. Another possible digest of sequence S could be D2, 1, 3, 4, 5. Again, we see that the first and last elements match those elements of sequence S, and every two consecutive elements in D2 also are consecutive in sequence S. Also, there is no element that appears twice in D2. What if you had a sequence that kind of starts and ends with the same value? So in this case, the digest would be this one, 1. Because the digest should not contain an element that appears more than once. So in this case, kind of the first element is equal to the first one. The last element is also equal to the last element. There are no duplicates, and any two consecutive elements in D, which there are not any, are also consecutive in S. Let me just say that any finite sequence S has a digest. And you can see this, you can prove this by using induction. So assume we have a sequence S, V1, Vk, let's say. Then for k equals 1, you have S equals V1, and the digest would be d equals v1. So kind of we have the base case. And now if we assume that for k greater or equal to 1, we have this to be the digest of S. So in this case, what would be the digest of the sequence v1, v2, vk plus 1? So there are two things to consider. Either vk plus 1 exists, is already in D, or not. So if it's not contained, so if vk plus 1 is not contained in D, then we can have this to be the digest of this sequence. If it's contained in D, so some element in D is equal to vk plus 1, then we can exclude everything that appears after vk plus 1, and this would be the digest of this sequence. So any finite sequence S has a digest. So after describing the notion of a digest, let's go back to the atomic single reader, single writer register that is being built out of a finite number of bounded single reader, single writer regular registers. So let's say we have such a construction, and we take this atomic single reader, single writer register, and we kind of create the following execution. First, we are going to call, let's say on this atomic register R, and we're going to write value 1, and then we're going to write value 0, and then we're going to write value 1 again, and so on and so forth. So if we take this write that writes value 1 to the atomic register R, and we look into it, so we're going to have something like this. What we're going to see is that this write operation performs writes as well to the underlying regular, to the underlying base registers. So we're going to have some write operations here, 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 and here, let's say, that are to the underlying regular registers that our construction works. Similarly, if we take another write here, the one that writes 0, and we look into it, we again will see some writes, right? That maybe a different number of writes that again write to those underlying base registers. So if you think about it, at this point here, all the base registers that our construction uses are in some specific state. So we can kind of think that here, let's say, D0 corresponds to the state of all those base registers. And after this first write, then we're going to have a state, let's say D1, and so on and so forth. So here it could be D2, here it could be D3, here it could be D4. And what to think about it is this, that this is just a value. And exactly those states here elicit a sequence. That could be this one. So here again we see the execution that we had before, slightly elongated, and we only care about the writes that write value 1. So this one, this one, this one, this one, and so on. So as we said before, each write writes to the underlying base registers. So we have here some writes, and here some other writes, and so on. And we can consider that this sequence of writes and the sequence of states that they produce create some sequences. S1 here, let's say S1, 2 here, S3, S4, and so on. So S1, as we saw before, corresponds to the state of the base registers before any write takes place, let's say D0. Then after the first write, D1. Then after this write, D2, and at the end D3. And here S2 could be, let's say, D0 prime, D1 prime, and so on, D4 prime. And this is where digest come into play again. So before we said that any sequence has a digest. So here we have a sequence, here we have another sequence, another sequence, another sequence. So let's say we get the digest D1 of this sequence, and we get the digest D2 of this sequence, and a digest D3 of this sequence, and then a digest D4 of this sequence. And now we argue that there exists a digest D, D0, D1, Dm, with m greater or equal to 1. So D contains at least two elements, that appears infinitely often in the infinite sequence of digests D1, D2, D3, D4, and so on. So why is this the case? Okay, we just cleaned a bit the screen. So what we said is that we have this digest D that contains at least two elements, m is greater or equal than 1, and this D appears infinitely often in this infinite sequence of digests D1, D2, D3, D4, and so on. And recall that D1 corresponds to the digest of some sequence S1, where S1 corresponds to the sequence of state of base registers that were performed during this write operation. So we have to answer two questions now. What does D appear infinitely often in this infinite sequence of digests? And why does D contain at least two elements? So let's see first this question here. So assume we have a digest that has length 1. This digest comes from some sequence Si that was generated by some write operation that writes 1. Notice that all those D1, D2, D3, D4, and so on come from operations that write 1, as we can see at the top of the screen. So for this to be the case and for Di to be equal to 1, what should be the case for Si? It should start from some state of base registers D, and then it might go through some other states, and eventually it will end up in state D again. So here at the beginning it was in state D, kind of the state of all the base register corresponds to D. Then it might have gone to D prime after the first write to some base register, then to D double prime, and then at the end again back to D. So let me just clean it up a bit here. Now recall that this write that writes value 1 is between writes that write 0. So before there was some write that wrote 0 to this atomic register R, and afterwards there was another write that wrote 0. So what we can do now is the following. We can inject some read operations here. So we can have a read operation here and a read operation here that read the atomic register R. So since this is an atomic register, right, this read takes place immediately after the write of value 0. So this read should return 0. And this read here takes place immediately after a value 1 was written, so it should return 1. But notice that those two read operations read the exact same base registers, because here we are in state D, and here we are in state D again. So this is a contradiction. The digest should have lengths at least 2. So now we can answer the second question. Why this digest D appears infinitely often in this infinite sequence of digests D1, D2, D3, D4, and so on. So the important thing here to notice is that we assumed in this construction that this atomic register R is implemented by using a finite number of bounded regular registers. And the way to think about it is that, let's say you had a sequence, an infinite sequence of finite values. So you had 1, 103, 205, 107, 10, 103, and so on and so forth. So we know that there would be some value, let's say x, that appears infinitely often in this sequence. So the same idea applies here, meaning that this digest D appears infinitely often in this sequence of digests. Just a final notice, recall that the digest cannot contain the same value more than once. This is also needed for the full proof, but we're not going to delve into it. We can now go to the meat of this video, which is the impossibility result. Again, just to remind you, the impossibility result states that there is no way you can implement an atomic single reader, single writer register out of a finite number of bounded regular registers where the read operation does not write to those underlying base registers. So this is again the impossibility result we want to prove. So a common way to prove impossibility results in distributed computing is simply by contradiction. So assume by way of contradiction that we can create this transformation, this construction, where we built an atomic single reader, single writer register out of a finite number of bound regular registers, and where the read operations do not write. So we assume this by way of contradiction, and we're going to lead to a contradiction. And this is how we're going to prove our impossibility result. Let's consider again the execution where we have this flipping execution where we first write 1, then we write 0, then we write 1 again to this atomic register R, then again 0, and so on. And then we said that we only take into consideration the writes that write 1. And those writes kind of write to the underlying base registers, and this creates a sequence S1 that corresponds to the state of the base registers at the beginning before any write takes place, and then during, let's say, those two base register writes, and so on and so on. And then we can get the digest of this sequence S1. And then we have a digest for this sequence here, and a digest for this sequence here, and then another digest here, and so on. So we get this infinite sequence of digest as we said before. And then we showed that there is this digest D that appears infinitely often here. Now if this digest D consists of D0, D1, and Dm, and this digest D appears infinitely often here, we know that those state of the base registers will also appear infinitely many times in this execution. So let's clean this a bit and rewrite some things. So we have D equals D0, D1, Dm, and we said that D0 appears infinitely many times in this execution. The same applies for D1 and so on, the same applies for Dm. So we have this execution, and since we know that Dm appears infinitely many times, let's say it appears here, and then Dm minus 1 would also appear infinitely many times, so let's say it appears here, and so on and so forth, and then we get D0. So now for this Dm, we're going to inject a read operation that we're going to call R0. So this read operation, when it reads the underlying base registers, it reads the state of the registers as it is in Dm. And then for state Dm-1, we inject a read operation as well that we call R1. And we keep doing this, and for D0, we have another read operation that would be Rm. So recall that we assume by contradiction that we created this transformation where the readers do not write anything. So by injecting those reads here, we do not change the way that the writes perform writes to the underlying base registers. So the writers don't even understand that there are readers taking place in between them. So now notice the following, that this read R0, when it reads the register, it will get back 1. Why? Because it reads the base registers in the state Dm. And we know that Dm is the last state of an R.write1 operation. Why? Because it's the last element in this digest, and this is the digest of a sequence of a state of regular registers for the write1 operation. And this was exactly why the first property of the digest, that the last element is equal to the last element of the sequence, was useful. And we're going to see in a bit why the fact that the first element of a digest is also equal to the first element of the sequence is also useful. Okay, so we know that this first read, R0, will return 1. And now we want to prove the following, that for every j from 0 till m, Rj, the read Rj will return 1, will give us back 1. And we are going to try to prove this by induction. And let's assume we succeed in proving this. So we already have the base case that the first read will return 1, If we prove this, then this means that Rm should also return 1. But notice that Rm corresponds to D0. D0 is the first element in this digest. So it's the first state of the regular registers before any write takes place. So if we execute a read on this state, we should not get back 1, but we should get back 0. So if we prove this by induction that all of those reads are going to return 1, then this would mean that Rm would also return 1, but Rm should return 0. So this would be a contradiction. And we would have proved our impossibility result. So let's see how we can prove this. So for simplicity, I'm going to draw this execution like this without depicting all those write 1 operations. And we said we're going to have dm, then dm minus 1, and then d0. And for dm, we're going to associate read operation r0, for dm minus 1, operation r1, and so on and so forth. And for d0, we're going to associate operation rm. And for simplicity, just to convey the idea of the proof, let's just say m equals 3. But that's kind of just for conveying the idea. So let's clean it a bit. So what we're going to have is d3, d2, d1, and d0, and we associate d3 with r0, d2 with read r1, d1 with read r2, and d0 with read r3. And we already saw that for r0 we know this will return 1. So this was kind of the base case of our induction, right? So let's assume that read rj also returns 1 for some j that is smaller or equal to 2 and greater or equal to 0. Again, this is just an example to convey the idea. And we're going to show that rj plus 1 also returns 1. So we have to remember now that we have this digest that corresponds to d0, d1, d2, and d3. And this digest appeared infinitely often in our execution. So we're going to also have infinitely often in our execution at some point, let's say d1 and then d2. And what divides those states is some write to some underlying base register, and this corresponds to a write that takes place inside this write operation. So if we take, let's say, concurrent with this write that writes something to the underlying regular register, if we take here and we inject read 1, and we also have here in parallel with the write read 2, what can happen? So this read 1 here, because it's concurrent with the write to a regular register, so notice that this is a write to a regular register, this one here, it could read the new state, which is d2. So r1 would read what it gets back from d2. So we're in this scenario here. And by induction, we know this would return 1. Therefore, this read here r2 will also return 1. Why? Because those reads here are to the atomic register r. So since this is an atomic register, if this returned 1, the next one should also return 1. So here R1 returned 1, and then this way we showed that R2 also should return 1, which is kind of what we wanted to show here. That if we assume that Rj returns 1, then Rj plus 1 also returns 1. So if we extend this idea to our original execution, then R3 would return 1. But as we said at the beginning, this cannot happen. Because in state D0, a read should return back 0. So this is a contradiction, and we have proven our impossibility result. So this was pretty complicated to prove this result. So hopefully this video gave you the intuition on how the proof went. If you want to see exactly and more carefully read the proof, I suggest you have a look at the book.